Alrighty, squad, in front of you I got problem 1.7 of Griffith's chapter 1. This is when you learn about expectation values. Here's the expectation value of P, which is the momentum, and we're asked to compute the derivative, time derivative specifically, of the expectation value of momentum. And they give us the answer, so it's basically prove this right here. And then they give us a little comment here. This is an instance of Ehrenfest's theorem, which asserts that expectation values obey the classical laws. So in classical mechanics, we have the derivative of momentum, which can be expanded into the derivative of mass times velocity. And here, mass can be pulled out of the time derivative. And the derivative of velocity is acceleration, which equals Newton's second law, F equals ma. But there's another way of writing the force, and that is the negative gradient of the potential. So if you have some kind of potential energy function, you can find its gradient, which means how fast it changes with respect to position. Normally this potential function is a function of x position, but it could be a function of other variables like, I don't know, time, temperature, whatever, stuff like this, right? So this is why you have a partial derivative here. But if it is only a function of x, then you can take a full derivative, and you take the negative of that, you get force. So this is a classical law. And if you take the expectation value of this operator, it is equal to the time derivative of the expectation value of the momentum. All right. So Ehrenfest theorem is pretty cool. It's a way of connecting classical mechanics to quantum mechanics. Now, how do you actually prove this? Well, we saw that the momentum operator is equal to negative I h bar partial x. So if you want to find the expectation value of the momentum operator, you basically sandwich it between psi star and psi and integrate over all space. So negative infinity to infinity. So over here, we put the momentum operator, which is this thing here. This works with any operator. So we could put some random operator. Let's call this operator capital O, and this operator acting on psi, and this integral over all space between psi star and psi with the operator sandwich between them gives you the expectation value. All right, so given this part right here, we can kind of assume that the way of writing this right here, expectation value of this, using the equation I wrote above, is going to be just sandwiching that thing between psi star and psi. I'm just going to put brackets over here because there's a negative sign. If I just have a floating negative sign, it's going to be kind of weird. And then, boom, dx. All right. How do you actually compute this? Maybe it's a bit complicated. We don't know. So we have to figure out how to compute this integral right here with the momentum operator and manipulate it a bit. Well, actually, we do have to take a time derivative here. So check it out. I've basically written this equation here in the expanded form using this operator thing. Get rid of some lines here and make it look a bit more clean. So we have the momentum operator, and if we use this general form of finding expectation values of operators, this right here, just this part, is how you can find the expectation value of the momentum operator. Then if we take this time derivative, slap that on, this Ehrenfest theorem tells us that it should be exactly equal to this, which is equal to this. Okay, how do we do this? You could check in the book. You could plug the momentum expression here, start taking derivatives of things, start simplifying things. And we can definitely do this, but for this video specifically, I wanted to show you guys the solution. And you'll see sometimes the solutions to these are very confusing. So there's two ways you could study. Either you check the problem like this, and then you just start attacking the problem with whatever way you see fit. This is a fantastic way of studying because you're going to run into a bunch of brick walls, and eventually, hopefully, with good luck and with good methods and no mistakes, you're going to get to the final answer. But if you don't get to the final answer and you're stuck somewhere, then you're not getting any kind of valuable information from this problem. Running into those brick walls is actually valuable information, but if you want to study a different way, and you can try both if you want, you can take a look at the solution to this problem and try to understand what they did. So that's what we're going to do today. I have the solution right here. I just checked Griffith's Solutions 3rd edition on Google. I found a big ass PDF, and over here is the problem. And you can see here they give you this. They expand it like this, and they pull out these constants. And then at the end they show you, boom, this equals this, which equals this, and they put QED. QED is something you put at the end of a proof. So since we're doing a proof here, we're trying to show that this is equal to this. At the end, you can write QED. All right, we're going to try to break down each individual line, everything happening in this problem here, and try to explain it to ourselves. If you don't like this, let me give you a reason why I think it's a cool way of studying, and maybe you will enjoy it in the future. So if you don't know what to do here, you can check the solution here. But just looking at the solution, like, you're just gonna skim over it, look at these lines, be like, oh, this looks crazy, and then you're gonna see that this is true, and then you'll be like, okay, cool, that's the solution, awesome. But if you look at the way these guys do it, it could be different from the way your professor does it, or your classmate does it, or how you've tried. So you can definitely get some cool information from just reading the solution. But you have to go very slowly and deliberately try to understand each individual thing being done in the solution. So we're going to do that here today. Hopefully it's a bit valuable to you guys. And I'm going to start out by outlining some important things. So right here is the thing that they're trying to solve for. What they've done is apply the momentum operator, which is negative I h bar, partial derivative with respect to x. Remember the sandwiching thing? What they do here is the sandwiching thing in one step, and they also apply this time derivative, right? You see the time derivative, except the problem is things here are functions of x. This is a function of x. You know that because you're integrating over x, right? So what happens in this line is actually two things in one step. First, they write down the expectation value between this psi star psi. So we have negative I h bar, partial derivative x, psi dx. Let's put some brackets here to fix that floating minus sign. And then they apply this time derivative. The time derivative is a full time derivative. You can tell this by the regular looking d over here. But once you use the, what is it called? Fundamental theorem of calculus. Here, the fundamental theorem of calculus says you can move this derivative and this integral and swap them. So basically take this entire derivative and move it inside the integral. This is allowed. So this is what they're doing here. They apply this derivative and they apply this momentum operator, and they sandwich the momentum operator between psi star and psi. Then they slowly move this thing in here. Boom, they move it here. Then they ask, does this depend on time? It does not depend on time, because this thing is only, well, it could depend on time. Yeah, that's an interesting thing here. You know what? I must say it actually does depend on time. So that's why they stop. Like, if this thing doesn't depend on time, you can move the derivative operator here, and then you can move it further in and further in. But actually, nothing here looks like it depends on time. If this does not depend on time, this one doesn't depend on time. And then this thing just acts on a constant. So the derivative of this stuff, which doesn't depend on time, is just going to give you 0, which is not what we're looking for. So this thing has to depend on time, because if it doesn't, you would get 0, and that's a brick wall. You're not going to get anywhere right if this whole thing here equals 0. All right, so they take this derivative operator and move it in, and then it gets stuck at this stage here. So you have to apply the derivative operator to this psi star. That's why they stop at this stage here. So the derivative operator moves in, boom, and this IH bar does not depend on X and it does not depend on T. So this IH bar moves to the front. You can see right here. Then they apply the momentum operator derivative, this partial X, which is right here, partial X. They apply that to this because derivatives work from this way onwards this way. This derivative operator is not going to apply here. It's only going to apply here. So they combine it like this. Then they have a psi star right here. Boom. So the derivative now becomes a partial derivative with respect to time because these things depend on position and time, right? Here you're taking a derivative with respect to x only. That's why it's a partial derivative. Here you're taking a derivative with respect to t. And the cool thing is, this derivative with respect to t is being applied to this product over here. So a lot of things have happened in this first line. Try to explain this to yourself. Let's keep reading. But noting that second derivative with respect to psi, second derivative of psi with respect to position and then time is equal to the second derivative of psi with respect to time then position. So this you can interchange, and then it says using equations 1.23 and 1.24. I don't know what those equations are. I'm going to check probably in a second and see. But let's see what's going on right here. Okay, so it looks like they're just isolating this thing here in the middle, and they're trying to solve for it here. Once they get a solution to this, they can plug it back into this integral and see what happens from there. So for now, I'm not really going to care about this too much because it's not, I don't see where it's being used. From here, it's not being used. You literally just take this, boom, and then you continue this way. So probably somewhere in this line, they're going to use this fact over here. Otherwise, why are they mentioning it? Another thing is these equations, I don't know what they are. I'm not going to look at them right now because it doesn't really matter. Maybe we're not going to need them. All right, let's take a look what's going on here. We have a time derivative of this product. So the product is this thing and then this thing. The derivative of a product is the sum of the derivative of each component times the other component without a derivative on it. So basically, this derivative, it's applied to only this, right? And then you just multiply by this thing without adding the derivative on it. So here is the derivative acting only on the first thing. This is the time derivative. It's acting only on the first thing. And here is the second thing. Here is the second thing. There is no derivative. There is no time derivative acting on this thing, right? Then you sum the other way. So first we took the derivative on this. Now we're going to take the derivative on this. So you can see this thing stays the same. This thing stays the same. And the derivative operator is only going to be applied to this second thing now. And here is where they use this rule. So before you had partial psi, partial x, and if you apply the time derivative, it's going to be partial t, right? That's this derivative being applied to this thing over here. But what they're saying is this thing, using this principle over here, you can interchange the x and the t derivatives. So first is the x, then is the t, then you can switch it to the t, then the x. So that's what they do here. They apply the time derivative first onto this psi, and then they move out this derivative that was there from the momentum operator, from right here. They just move that over here to the side, and they're going to apply this later. Nice. So this is the first step. Why are they doing this? Because this thing is actually something you know. This is part of the Schrodinger equation. Let me see if I remember the Schrodinger equation. So I know that there is there's an h bar. I know there's an IH bar. A psi dot is equal to the Hamiltonian operator acting on psi. So if we expand this, there's an IH bar. This dot is a derivative with respect to time, and it's a partial derivative because psi is a function of time and position. So it has to be a partial derivative. Then here, the H operator, the way you can expand the H operator is the T operator and the V operator. The V operator is just V, so we could do plus V times psi. And the T operator is the kinetic energy. So in classical mechanics, the kinetic energy is p squared over 2m, or you can write this as 1/2 mv squared. But if you switch p is equal to mass times velocity, and then you square that, you can plug it in here, you get p equals 2m. And we know what the momentum operator is. It is right here. So basically, basically, take this momentum operator, square it. So what I have is I squared and a -1, but the minus gets squared. Hold up a second. There's a minus here. -1 h bar squared over, there is a 2m on the bottom. This 2m comes here. And then this derivative is a second order derivative with respect to position. So this is the Schrödinger equation, h bar squared 2m partial second partial with respect to x. Let me erase all this stuff here. Erase this. All right, so this is the Schrödinger equation. I remember it like this because this is like less symbols, and then I expand this into the position, or sorry, the time derivative, and I expand h into the kinetic energy. So the Hamiltonian is the kinetic energy plus the potential energy. Hamiltonian is the total energy. This is the kinetic energy operator acting on psi, and this is the potential energy operator acting on psi. The potential energy is left like this because we don't know what the potential energy is. It could be anything depending on what your system is. And that's kind of cool because that's what we're looking for over here. So using this equation, we found a way to introduce V into this. Awesome. Now, why is this important again? Remember when we left off here? This partial psi partial t is literally right here, partial psi partial t. So if you want this, you just isolate it. Just move this IH bar here. It gets distributed onto both sides, and that's what we have over here. So if you divide by h bar, one of these h bars, which is squared here, gets canceled. This 2m stays the same. Here we have partial derivative, second order partial derivative with respect to x, second order partial derivative with respect to x. And notice that here, they're actually applying it to the psi star. So that is why we have a psi star over here. They also apply it to just the regular psi, and you will see that here. So the Schrödinger equation gets used twice. One time over here, and one time over here to expand these equations. Nice. This minus sign stays, and this I is over here. Boom. And when you have an I, since you're dividing here, when you have an I in the denominator, an I in the denominator can be multiplied by I in the numerator. So let's say this is 1 over I. I can multiply by I on the top and I on the bottom. I'm just multiplying by 1 because I over I is 1. So this is okay. Then here, I squared, this thing can be replaced to -1. So basically, I in the denominator is equal to -I in the numerator. So that's what happens here. And you get this extra negative sign because the complex conjugate version has an extra minus sign there. Okay. Then here we have another I. This comes from here. An I in the denominator equals -I in the numerator. And this minus turns back into a plus because the complex conjugate carries an extra minus sign in front of it. Nice. Now, we have replaced this with this, right? You see that? Boom, boom. So we just multiply this afterwards. We just multiply by this afterwards. Great. Now we have a plus. We have a plus. Here we have psi star. Here we have psi star. Position, partial derivative. Position, partial derivative. And this thing you replace with the thing from the Schrödinger equation. You just isolate it. Move this I and h bar on the other side. I and h bar moves to the other side. Here we have a 2m. Here we have a 2m. And here we have the partial derivative, second order. And here we have a minus v psi. And the v is also here. So you can see how this equation here, first we took a derivative of a product. We expanded using the product rule of derivatives. And then we just take the Schrödinger equation and replace this. Because this comes from the Schrödinger equation. Amazing. Now this whole second line is understandable. So you can see this whole problem is solved in basically 2 lines. One line here, one line here. And maybe another line here, and maybe this line over here as well. But basically the big chunk is these 2 lines. And we've already understood one of them. Crazy. Now let's keep going. And it looks like here they're skipping a bit of stuff, but what is happening here is they are pulling out some constants. So they pull out IH bar is pulled out from over here, boom, and a 2m is pulled out. And at the same time, this derivative is applied here and applied here. So this derivative is with respect to x, and here this derivative is with respect to, interesting. What is going on here? It looks like they switched the terms. So this term here actually becomes this term. So term 1 here becomes term 2, and this term here, term 2, becomes term 1. Pretty goofy. Why are they doing this? Well, take a look at this. Here we have a psi star, right? Here is the psi star. Here we have a position partial derivative. This gets applied inside to this term and to this term. And this derivative acting onto this second order derivative now changes this to a third order. And here is the third order derivative. And what the derivative is taking, or what the derivative is acting on, is just a psi here, right? You see that? Nice. Here we pull out an IH bar over 2m. IH bar over 2m is pulled out. So here we have no constants. The constants that were first here get pulled out to the front here. Here we pull out some constants. So an I is pulled out and an H bar. Is there a mistake here, bro? Let me see. Because we pull out an H bar here, but then there should be an H bar squared over here, huh? Is that true? Because there's an H bar in the bottom and they pull out an H bar from the top. Because if you distribute this here, you get an H bar here and an H bar here. But here, the H bar was on the bottom. So yeah, this might be a mistake. Very interesting. But if there's a missing constant, sometimes things still work out. So we're just going to keep grinding and see what the problem is. This operator gets applied here. We already saw that. And then it gets applied here. So here, it is being applied right here, right? Interesting. It's a little weird, guys. Where is this second order thing coming from? Oh, man, I see what they're doing. They literally expanded. So you see here how we have one term, two terms, and then here we have one term, two terms. This is four terms, right? But over here in the first big brackets, we have a V, and over here in the second big brackets, we have a V. These guys are blocked off by these V's. This guy in the line here actually takes this V and this V, and he keeps them in the second term. So here is the V term from this, and here is the V term from that. And over here is the terms that appear in the first thing over here. So this one, which is third order, can be seen over here. And this one, which is second order, can be seen here. You see partial second order, psi star. Here we have partial second order, psi star. So that is where the second thing is coming from. That's why these, when you pull these things out, it makes sense. And there's a minus sign here, and this minus sign is over here too. Great. And remember, we applied this here as well. So this thing can be seen over here. Okay, now that makes sense. Nice. Now we add I over H bar. This is pulled out of here, and that's great because we have an I over H bar here. This one is positive, right? There's a positive sign here, so this one is positive. But the other one right here is negative, so there's a negative sign here. And we have a V and this, and then we have a derivative acting on that. Derivative is acting on that, right? It gets applied inwards. And we have a psi star, psi star. You guys see how everything is organized here? Okay, now it's literally just redistributing terms. Distribute terms in whatever way you see fit. This is why I didn't want to do this problem. I just wanted to read the solution because I feel like I'll get some more value by reading how they did it. And let's keep reading here because they do something probably pretty crazy here. The first term integrates to 0. So what he's saying is this term here, or perhaps this term. It's a little unknown which term he's talking about. Maybe this term, maybe this term. All right, so that equals 0, using integration by parts twice. And the second term can be simplified. So I'm assuming this term is being simplified because he uses v psi star. Here there's a v psi star. You see the v psi star. And there's a partial derivative of just psi. Then there's a minus sign, minus sign. Here there's a psi star, psi star. And then you do a product rule here. So remember when we did product rule here? We took the derivative of the first thing times the second thing, derivative of the first thing times the second thing, plus derivative of the second thing, derivative of the second thing times the first thing, times the first thing. So right here, we have to do the same thing. Derivative of the first thing, right? Here is derivative of the first thing times the second thing, plus derivative of the second thing, times the first thing, But since there's a minus sign here, if you put brackets and then you do your product rule here, the first thing plus the second thing, this minus sign applies to both, and both will have a minus sign here. You see how there's two minus signs? Nice. So this thing here is expanded like this, and he says you can simplify this whole thing here, which is written over here, into this. Okay, so there's a couple things happening. First of all, how do you simplify this into this? That's very important, and it's not done for us. So this is why going through the solution is important, because you're going to see some stuff that's not done for you. And the second thing is, the first term integrates to 0 using integration by parts twice. So this thing right here, he says that this whole thing goes to 0 because integration by parts is used. Interesting. Now, how does that make sense? And which one should we tackle first? Okay, let's say we accept that this goes to 0, right? And maybe we should do a practice on integration by parts. Let's check now how this thing simplifies to this, because from here, it's pretty easy to get to the solution. Okay, so let's see what they did here. Here we have a minus psi star, or absolute value squared of just psi, times the derivative of v with respect to x. So here is the derivative of v with respect to x. Here is the derivative of psi with respect to x. All right, so this is the only thing that we're left with. Actually, this is what we are looking for, because minus sign is here, psi star, psi is equal to absolute value squared of psi. And then here we have what we are looking for. So this last term is equal to this. That means these first terms must cancel. How do they cancel? It actually looks like they're pretty simple. Here we have v, here we have v, here we have psi star, here we have psi star, and here we have derivative of psi with respect to x, derivative of psi with respect to x. This one is positive, this one is negative. It's literally just like a minus a. So this is a minus a. This thing equals 0, and all that's left here is this part. So this entire thing, once you expand the derivative using product rule, you get a bunch of cancellations. Maybe just 2 cancellations. And then we have this. So we saw that this whole thing simplifies to this, right? And remember where this whole thing came from. This whole thing was inside here, right? So what we've calculated is this thing here, and we saw that that equals this. Now let's plug it back into the integral. So this whole thing gets replaced, integral with respect to dx, and we have a minus I h bar. So here we have the minus I h bar, right? And here we have an I h bar from this thing, right? So that gets pulled out. That is supposed to be here, but he simplified just the things inside the brackets here. So this IH bar is important. The IH bar comes here. The H bar cancels with the H bar. I times I equals minus 1, and minus 1 cancels with this minus. So this whole thing just equals 1. Nice. Here we have the derivative with respect to x, or sorry, the integral. Here we have the integral with respect to x. And this whole thing inside, it gets replaced by this. And there's a minus sign here. Okay, I guess that makes sense. So we have a minus sign, this thing here, and here they're literally just using the operator thing. So the operator thing that I showed you guys before, if we have psi star here and some random operator, dx, this is equal to the expectation value of the operator. It's what I showed you guys up here. So if you have this sandwich between these guys, it could be sandwiched between these guys, but if you combine these guys together, it gives you psi absolute value of psi squared. So that is what we get here. Okay, I guess that makes sense. Maybe we learned something cool, but one important thing is the first term integrates to 0 using integration by parts twice. This is the only thing of the solution that does not make sense to us. So it's going to be a good practice if we take this, we have an IH bar here, 2m, and we have psi star. I'm just rewriting that thing here. This is with the third order derivative. Nice. Here we have minus sign, squared, psi star. Here we have partial x squared. And here we have partial psi, partial x. Okay, integration by parts. How does this work? How I remember integration by parts is uv, integral of uv is equal to, no wait, integration of uv, oh, man, I actually don't know, but I remember the integration by parts rule is uv minus integral of v du. Okay, I'm actually unsure here, but what I can imagine is happening is you use integration by parts, and if you apply it to this, right, you can convert this psi star times third derivative with respect to x of psi, and you can kind of move the derivatives onto the other thing. So here we move one of the derivatives. Right? And then we apply integration by parts here as well, and we move another derivative to the psi star. So here we are just left with one derivative on the regular side. Now if we're left with this, check it out. This thing, all right, this thing here used to be this thing. And if we do this thing, which is this, minus this, they are the same thing. Here we have second order derivative with respect to x of psi star. Here we have second order derivative with respect to x of psi star. And it is being multiplied by a first order derivative with respect to x of psi. Same thing here, first order derivative with respect to x of psi. So this thing minus this thing, this equals 0. There is some steps here in the integration by parts that I'm not talking about, but I'm going to leave this for you guys to take a look at if you're interested. How do you convert something of the form this into the form this? How do you apply integration by parts onto this? Take a look at it. I hope this video was pretty interesting, just reading through solutions. If you have a solution manual, or if you do a test or a quiz and you have no idea what's happening, you want to go through the solutions like this. I'm not going to bore you guys with doing some math over here because the main interesting thing is the physics. But once you guys are studying, you want to slow down and ask yourself questions about each individual line happening here. These equations, we didn't bring them up, but I swear to you, there are two equations related to the Schrodinger equation. This is one of them, and there's another one for the psi star, and that was used over here and over here. So we talked about a lot of things. The momentum operator, this thing, expectation value of some random operator sandwiched between psi star psi. We talked about the Schrodinger equation. We did some product rule, expansion of derivatives. We did some manipulation, right? Right here, there was a lot of manipulation, moving around terms. Some of the terms came here, some of the terms came here. And then one thing that is not being mentioned is this integration by parts. So take a look at that. If you guys are interested, let me know. I'll do a video on this. But I hope you guys enjoyed this. Try to go through solutions like this on your own, and you're going to learn a bunch of shit. If you don't know something, like you don't know how this integration by parts is, write it down in your notes, and then put a reminder on your phone saying, yo, I need to learn how integration by parts converts something like this into something like this. And then go over the solution several times. If this didn't make any sense to you, read it a couple times, try to do the problem by yourself. Now that you read the solution, maybe open up this problem and start from nothing. Here, you're given literally nothing. You're just given this. You don't know about this, you don't know about this, and you don't know about the Schrodinger equation. These are extra things you have to pull out of your ass to solve this problem. So try this out, because the only way you can remember these things is if you recall them while you're using them. But the only way you can learn them is if you look at a solution or you read the content in the book. I hope you guys enjoy this. I'm going to do another problem. Try this integration by parts thing on your own and see if it makes sense. If you don't know about it, Google search integration by parts. Try to see it, how it fits. And if you still don't know, send me a comment. I got you guys. Thank you guys for watching. See you in the next video. Peace.